Namaste. Myself is Girishas, working as a lecturer in electrical and electronics engineering at Government Polytechnic, Ushalnagar. Today, I am going to discuss about the topics switchgear and protection. In this switchgear and protection, the first unit is fundamentals of protection. So fundamentals of protections, in this fundamentals of protection, the third topic is importance of calculation of short circuit current. Before I will discussing the importance of calculation of short circuit current, first I will explain the fault occurs in a power system. In power system, the fault may occur by sudden failure of any power system equipment or by accidental damage or short circuit to a overhead line in the power system. When a short circuit occurs, the current in the system increases to an abnormal high value. At the same time, the system voltage reduces to a low value. The short circuit in the system may lead some of the following effects. First one, heavy current causes a excessive heat which results in the explosion sometimes. And second one, the short circuit forms an arc in the power system and causes to damage the power system element. Next, third effect, stability of the power system is varied. And fourth one, damage to the other equipment connected in the power system. Due to the short circuit, the system voltage decreases to a low value, which will cause the protective relay coil failure. So these are the some requirements for short circuit occur in a power system. So next, a very important topic, the importance of calculation of short circuit current. So first, what is the necessity for calculation of short circuit current? So it is necessary to know the maximum possible value of short circuit current in the power system, because the power system having different equipments are connected. So these equipment ratings are calculated or selected. The short circuit current is very important. The second one, the magnitude of short circuit current determines the equipment settings, equipment rating settings, types, as well as the locations of the power system. So next one, the magnitude of the short circuit current. It determines the size of the protective reactors. So what do you mean by reactors? Reactor is a coil which connected in series with the power system to avoid the short circuit current. And next point, the important calculation of short circuit is the proper selections of the power system equipment. The proper selection of the power system equipment means the power system having different equipments connected. such as busbar, current transformer, and power transformer, feeders. So these equipments are mainly depends upon the rating of the short circuit current. So another important definitions, percentage of reactance. So percentage of reactance is very essential for every equipment or every element equipments connected in the power system. So it is defined as the total phase voltage dropped in the circuit when full load current is flowing through the system. So the formula for percentage of reactance is I into X divided by V into 100. I into X V divided by 100. Here I is called full load current flowing through the system, and V is the phase voltage dropped in the circuit, and X is the reactance in ohm for phase. The percentage reactance can also be expressed in terms of kVA and kV. kVA means kilovolt ampere and kV kilovolts. kVA is the rating of the transformer as well as the generator alternator, and kV is the rating of the transmission lines. So the percentage of reactance in terms of kVA and kV is kVA into X divided by kV squared into 10. So this is the derived formula for calculation of percentage of reactance in terms of kVA and kV. Here, as usual, X is the reactance and kVA and kV are the respective ratings of the equipment in the transmission line. So another important definition, base kVA. So what do you mean by base kVA? In a power system, having various equipments are installed at different kVA ratings. Therefore, it is necessary to find the percentage of reactance of all the elements on common kVA ratings. This common kVA ratings is known as base kVA. Therefore, the formula for calculation of base kVA, that is percentage of reactance at base kVA, is equal to base kVA divided by rated kVA into percentage of reactance at rated kVA. Usually, the value of base kVA depends upon the largest plant of the power system value and equal to the total plant capacity and any arbitrary value in the power system. So next, one of the examples I will take on for discussion illustration. What is the required necessity for selections of the common base kVA in the power system? So here one of the examples, for example, you can consider a three-phase transmission line operating at 66 kVA. So 66 kVA is the transmission line and are connected through a 1000 kVA transformer. So 1000 kVA transformer is one of the equipment installed in the transmission line with having a 5% reactance to a generator station busbar. So this transformer of 1000 kVA with 5% reactance are connected in a busbar of a generating station. Another one is the generator having 2500 kVA with 10% of reactance. So here the figure shows a single line diagram. Suppose the single line diagram. In this line diagram, so here So three equipments are appear. One is called input. One is in the input side is called generator. Another one is transformer. So another one is the transmission line. So here the common base kVA is selected. So here the first steps is, suppose we have to choose 2500 kVA as the common base kVA on this value. So first we have to calculate the common reactance of the transformer and reactance of the generator as well as the transmission line. The reactance of the transformer at 2500 kVA of base, 2500 kVA of base, the formula is reactance into base kVA divided by rated kVA. So rated kVA of the transformer is 1000 kVA and common base kVA is called 2500 kVA. So the base kVA for generator is considered as a, so rating of the generator is considered as a base kVA. So therefore the reactance of the transformer at 2500 kVA base is 12.5%. Similarly, the reactance of the generator at 2500 kVA of base is 10%. So therefore the total percentage reactance of common base kVA of the given power system is 12.5 plus 10 is equal to 22.5. So next, the full load current corresponding to the 2500 kVA of base at 66 kV is given by I is equal to, so here formula P is equal to root 3 V into I. Therefore I is equal to P divided by root 3 into V. So P is called the rated base kVA and V is the transmission line voltage. So therefore I is equal to 2500 into 10 to the power of 3 or 1000 divided by root 3 into voltage of transmission line is 66 kV. So therefore the load current flowing through the transmission line is 21.787 amperes. Next, the short circuit current. So the short circuit current is equal to the formula load current into 100 divided by total percentage reactance of the system. The total load current is 21.87 and percentage of reactance is, that is total percentage reactance of the power system is 22.25. Therefore the short circuit current is 97.2. So this short circuit current is for the common base kVA of 2500 kVA. So next, now suppose we have choose 5000 kVA as the common base kVA. So here the reactance of the transformer at 5000 kVA base is, as usual formula, the reactance of the system into common base kVA divided by rated base kVA. So the reactance of the transformer at 5000 kVA base is 25%. Next, the reactance of the generator. So the reactance of the generator again at 5000 kVA base is 20%. So therefore the total percentage reactance on the common base kVA is 25 plus 20, 45%. So again we have to calculate the full load current, the corresponding 5000 kVA at 66 kV transmission line is, again the load current I is equal to P divided by root 3 V. V is the transmission line voltage, that is P is the base kVA of the system. Therefore I is equal to 5000 kVA, that is 5000 into 1000 divided by root 3 into 66 kVA is equal to 43.74 amperes. Again the short circuit current for the choose of 5000 kVA common base kVA value is 97.2. If you observe the previously the first case, we have to choose 2500 kVA as a common base. So here the short circuit current is 97.2. So second case, again if you observe, suppose we have to choose 5000 kVA as the common base, again the short circuit current is 97.2. So from these two comparison, it is clear that whatever may be the value of base kVA, the short circuit current is same. So next, short circuit kVA. Short circuit kVA is defined as the product of the normal system voltage and short circuit current at the point of fault in the transmission line, and it is expressed in kVA, and so this kVA known as short circuit kVA. Here V is the normal phase voltage in volts and I is the full load current in ampere at the base kVA. Therefore, X percentage of X is equal to percentage of reactance of the system on base kVA up to the fault point. Therefore, the short circuit current is equal to the full load current in the system into 100 divided by percentage of reactance. So finally, the short circuit kVA is equal to base kVA into 100 divided by percentage of reactance. Next, the important topic we will discuss about reactor. So reactor is a coil, that means it is an inductive coil, it having number of turns. It is designed having a large inductance compared to its ohmic resistance. So the inductor coil is used to connect in series with the transmission line. What is the necessity? The reactors are connected in series with the transmission line because is limit the short circuit current and to avoid the any faults occur in the system. Usually the additional reactants are connected in series with the transmission line are called as reactors. So reactors are connected in different fashion. One is called, the reactors are connected in series with the generator in the transmission line. Second one is, it is in series with the feeder line, and third one is in series with the bus bar. So reactors is a limiter of the short circuit in a transmission line. So first the reactors are connected in series with the transmission line, in series with the generator in the transmission line. Second one, it is in series with the feeder line, and third one is it is in series with the bus bar. So another important topic is what is the advantages of reactor. So what is the main advantage of reactor is, so reactor we know are connected in series with the transmission line to limit the flow of short circuit current and then to avoid the any failure of the power system. So some of the important advantages of reactors connected in this power system is, reactors limit the flow of current. Reactor limits the flow of current and thus protect the equipments from the overheating. What do you mean by this? What is the advantages of this point? Means When a fault occurs in a transmission line, usually heavy short circuit current flows. At that time, the system voltage is dropped. Hence, as a result, heavy heating and also arcing and also damages occur in the power system. These reactors helps to avoid these unwanted requirements in the power system. So hence the reactors are connected in power system. Secondly, they permit the installation of the circuit breaker at lower rating. This is the most important because circuit breaker is a switching device. They having their current setting, they having their own current setting value. How it is say the circuit breaker is connected in the power system to break the fault section means the selections of the circuit breaker, it depends upon their magnitude of the short circuit current. So these selections of the circuit breaker depends permits type of circuit breaker is connected in the system permits the value of the reactors. And third one, usually short circuit occur in a system at any point in a transmission line, either maybe sending point or either maybe output point or middle point or maybe feeder line or maybe bus bars. So the fault location at any point in a transmission line, so that fault part is isolated from the given system, the reactors is connected. So from the observation of the reactors connected in the power system, the conclusion is that troubles are localized or isolated at any point in the power system. They originate without communicating their disturbing effect to the other part of the power system. That means the power system having different connected part, so other part of the power system is not affected from the occurrence of the short circuit. So the reactors here isolated the fault section of the transmission line part. So this increases the chance of continuity of the supply. Usually the reactors are the main elements in any type of power system because so this is the limiting device that means they limit the flow of short circuit current when short circuit current in the power system. So I will discuss about the power system importance power in a power system, the importance of calculation of short circuit current and definitions of the reactor and base kVA, then base short circuit kVA, then percentage of reactance. So I think it is enough. Thank you.